What's up, guys? As you can see, this is not the next page in the come on, get it, slideshow. Not the next page in the notes, but that's okay. Your flexibility today was awesome, and your ability to jump onto a harder set of problems with some enthusiasm was awesome. So let's go with it. We're going to start looking at what we call multiple mass systems. This one in particular, two masses hanging vertically from two pulleys, is called an Atwood's machine. It doesn't even have to be two pulleys; it can just be one pulley, where the blocks, just hang on either side of it like that. It's called, for whatever reason, an Atwood's machine. Feel free to go look up who Mr. Atwood was. So, what we can do here is, really introduce a method of analyzing systems like these where, multiple objects can be accelerating. Things we'll assume that the pulleys themselves are massless. All right, rotational kinematics, or really rotational dynamics, is not something we talk about in this course. But when you take C next year with Big and Tall, that's Mr. Kotz. Big and Tall, the big show, the big dance, Mr. Kotz. When you take that next year, you'll get into some rotational dynamics. So anyway, what we can do here is look at each of these blocks separately. It's one way of analyzing this. All right, and if we do that, what I would do is look at the blue one. I mean, literally, when I draw that little dotted line around something, what it says to me is I'm isolating that part of the system. I'm going to look at forces that act on that part of the system alone. So if I look at mass M1, what we have, so this is M1. We have, well, I'm going to call it M1G, the weight of that block. And we have this tension. Okay? If we look at block 2, if we do that over here, M2, we would have M2G and the tension. Agreed? Okay? Of course, I'm assuming that we're okay with I'm saying that W is mg. More and more, I'm not going to write W, I'm just going to write mg. Okay? These things that I love about you guys is your ability, in one step I do AX, and the next step I just write A cosine theta. You guys are getting used to that. No big deal there. So these little progressions in thought are great for us. Now, if we look at a net force statement for each one of the blocks, here's what we could say. Net force equals MA. Now, here's a big point, all right? What we have to do in questions like this is pick a positive direction, all right? And we're going to stop doing, for now, X and Y. What we're going to start doing is, this way or this way. Okay, if the system goes this way, well, why don't we just, for this problem, call that the positive direction? That would mean that if the M2 goes down, that's positive. If M1 goes up, that's positive. That can be a little tricky. So since for M1 going up is positive, we do T minus M1G equals M1A. Okay? And for block 2, we would say that, well, remember, if block 2 goes down, that's positive. So that's M2G minus T equals M2A. Right? You okay with that? Now, there's no numbers in here, but the typical way that these problems are asked are, what's the acceleration and what's the tension on the string? Now, if those are two unknowns, that's why we have two equations here. All right? But the big deal is that same string, same tension. All right? Objects are connected by a string, have to have the same acceleration. So if we want to see what their acceleration is, say, here's what I'm going to do. Well, each of these has the same tension, so I'm going to solve each one of these equations for tension. This one says tension equals M1A minus M1G. this one says tension equals M2G minus M2A. Make sure you follow the algebra. Well, again, since these tensions are the same, it means that this expression and this expression are equal to each other. So I will write them as M1A minus M1G equals M2G minus M2A. I want to solve this stuff for A. I'm going to figure out what the system's acceleration is. So I'll get all the A stuff on one side, all other stuff on another. This is M1A plus M2A equals M2G plus M1G. I don't know if you noticed, but I paused because I was like, wait a minute, something's not right. And here's what's not right right here. If I'm solving for t, that's got to be a plus. Everybody saw that, right? Good. So this is a plus here, which makes this a minus there. Apologies. Okay, we want to solve for a. Well, we have a in two terms here. We can factor it out of each term. That's a m1 plus m2 equals m2g minus m1g. Well, you know what I'm going to do? I'm going to factor out the g. Okay? So acceleration of the system is g times m2 minus m1 divided by m1 plus m2. No numbers, I know. Let's get used to those, right? So, depending on what those masses are, this one really says that if m2 is bigger than m1, right? If m2 is bigger than m1, then the top of this fraction will be positive, and that means that a is positive. And that means that, sure, it actually will accelerate in this direction that we chose as positive. That makes sense, right? If this mass is more massive than this mass, then sure, it's going to accelerate this way. If m1 is bigger than m2, then that means a is going to come out negative. And again, since we chose positive as this direction, if m1 is bigger than m2, then our acceleration is negative, and it means that this thing goes that way and m2 goes up. Make sense? Right? Right. Now, what we could do is take this this acceleration, and we could now plug it back in to, say, here, and figure out the tension on the string. It gets to be, the algebra there can get to be a little bit of a pain. Or at least, what I will say is there's an easier way to do this. Why did we go through this whole slide? Well, because we need to draw some connections. We need to be able to look at the fact that we can look at one block or the other, right? We can look at mass 1 or mass 2, right? It's important to be able to identify forces acting on individual parts of the system, all right? But, like we said, there's a different way to do it. Ooh, look at it go, sure. So like I said, we can look at each part of the system separately, or we can look at the system as a whole. And we can almost imagine that the system doing what it did here, right? The system doing that, accelerating that way, is almost like one object doing that. Don't you love that animation? I love it. So the system accelerating is kind of like the system, a bunch of stuff accelerating, right? And where we said, well, forces acting on the system, and if we sort of look at this as the system. Remember before when I just drew a dotted line around one block and said what's going on, coming in and out of that block, that box, that dotted line box? Well, coming out of the dotted line box now really is only this M1G, excuse me, and this M2G. What about the tensions? Well, the tensions, it's almost like, some forces in here, one part of the system pushing on a different part of the system. We actually don't care about that. All right? We don't care about forces that are internal to the system. Almost like when we talk about a person in a car, what makes the car go? Well, it's not the person pushing on the gas pedal. That's something going on inside the car, where really what matters is friction between tires and road. We don't care about internal forces. We care about forces of the exterior world interacting or acting on the system. So what I'll do is I can actually sort of represent this like this: M1G, M2G. All right, the way that I really end up drawing them is always like this, and literally drawing this force coming out like this, and this force coming out like this. But the way that I'm sort of thinking about it is like this up here. Okay? Where what we do here, if we look at the system, we can say that net force equals M system A system. Well, A is the same for each block, so I don't need the system there. So net force, I'm going to say M2G minus M1G equals M system. That's M1 plus M2 times A. So A is M2G minus M1G. Oh, wait a minute. I can factor out that G. So that's G times M2 minus M1 divided by M1 plus M2. And if you notice, this is the same exact expression we got to on the last page after doing a bunch of algebra and two equations, two unknowns, and solving for one variable and setting those two expressions equal to each other and blah, 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 blah. Well, we can do that all in one, kind of one step. Well, one combined step with a little bit of algebra. I like this one a lot easier. Now, if we want to find the tension on one of the strings, well, here's what we can do. To find tension, what I'll do now is I do have to do this on one object or the other, right? Because if we want to look at the tension, we can only look at part of the system where tension acts on that part of the system. So now I would do this. M2G. Tension, I would say the net force equals MA. In this case, it's only M2, right? We are looking in this little isolated part of the system, we're only looking at mass 2. I'm going to keep the same positive direction. Sorry, just T. Equals M2 A. So M2 times, well, I guess we'll just do this. G, M2 minus M1 over M1 plus M2. All right, so the tension is M2G, M2 minus M1 over M1 plus M2. Poop. Sorry. Well, I'll do this. I'll make it work, don't worry. So that goes over there. It really has to be this. M2G minus that equals the tension. What do you think? Not so bad? It's kind of the odds of us doing one of these problems without any numbers are slim. A little slim, at least. But this, you ought to be able to get here for sure. I've seen this. This is not an uncommon multiple choice question. Which of the following is an expression for the acceleration of a system, blah, blah, blah. So that one you should be comfortable getting to. Tension's a little more of a pain down here, but I think doable. Notice, just so we're sure, this is A, right? M2A. Right, here's our A from before. Okay? Okay. Let's use ours to calculate G. Well, I have one in the room. You'll see it tomorrow if you haven't seen it already. We're going to do a lab tomorrow to do an experimental determination of G using an Atwood's machine. Of course, we know what G is already, but watch how great of a result we'll get with a nice simple piece of lab apparatus and some pretty sweet pulleys. Oh boy, there it goes. Now here, this is one we talked about sort of in class, all right, but introduces some different concepts. Now, finding the system's acceleration. Well, again, the system, right? System means this. Let's look at all the stuff, or let's take all the stuff inside the box and sort of say, well, what acts on that stuff inside the box? Well, what acts on it is, well, without friction, let's see. It doesn't hurt to draw all our forces. Here's M1G. Here's a normal force. I'll call it N1. Here's M2G, right? Those forces are, coming out of the system, acting on the system. We don't care about tensions. Tensions are internal to the system. All right, so without friction, again, now I'm going to say this way is positive. Anything that goes that way is positive. All right, so if we do net force is M system A, well, the forces that work in that direction are M2G. That's it, right? Yeah, we have this M1G. Yeah, we have the normal force, but those are perpendicular to the direction of motion, or at least the direction of motion of M1. And they're acting on M1, so those do not get included in our net force statement. All right, equals M system times A. How much stuff accelerates? Both of those masses together. We have to use the sum of those two masses. So the acceleration of the system is M2G divided by M1 plus M2. Okay? If we include friction, right now, we say there's a frictional force here, and that amends, or what's the word, changes, I don't know, our net force statement. So now we say net F equals M system A. Now we have M2G minus that force of friction equals M1 plus M2, mass of the system, times acceleration. We could go a step further. M2G minus, well, mu times the normal force, N1, equals M1 plus M2A. We could go even a step further. N1 is equal to M1G equals M1 plus M2A. And we could write an expression for A here. So M2G minus mu M1G divided by the sum of the masses equals A. Okay? Yikes. Now, finding tension on the string, right? If we want to find tension on the string, I haven't left myself a ton of room, but what I would say is, like we said before, if we want tension on the string, you have to isolate part of the system, where tension acts on that part of the system, right? I like to do this one here because I don't have to worry about frictional force and writing stuff with mu's and all that. For the hanging one, which is nice, if we go over here with the simple one, we would say that M2G minus that tension equals M2 only times A, right? Only M2, right? In our little dotted black box here, M2 is the only part of the system, well, the only mass that we're looking at when we look at the forces acting on that part. Okay? Well, I'll put A in here. A is, well, M2G over M1 plus M2. so that we can write an expression for t, right? I'll trust you can do that algebra. Same thing would happen over here, right? It's actually the same exact, the same exact phrase over here. It's m2g minus t equals m2 times this a, right? A little different a, because now we have friction, and m2g minus mu m1g over the sum of the masses. Again, I'll assume that you can write an expression for t. Just do the little bit of algebra. What do you think? Not so bad? What else? This, I think, is our last slide. It is our last slide. So these will get a little trickier when we start to do, well, I guess, how much trickier can they get? I guess they could, what could we do? Oh, yeah, we could do one, we could do one where, hang on. You don't have this slide, of course, but there's, I could certainly imagine one that looks like this. Pulley, rope attached to a mass, right? Mass here, whoops. Right, and then there's friction here. That could be a trickier one. I'll find one of those for you to do on a homework. But yeah, the idea with these multiple mass systems is you have to be able to write, write net force statements for the system, right, including all of the mass that's accelerating, and forgetting about forces that are acting inside the system or forces that parts of the system exert on each other. And then you have to be able to write net force statements for individual elements of the system. If you want to know things like, well, what's a force that acts within the system, or a force that part of the system exerts on another part. That can be tricky, right? Knowing which masses to include or not to include. Certainly tricky. But you did a great job at that today. At least block 1 did. It's only block 2 right now, so block 4, we'll see how you did. But my confidence is pretty good. All right, folks. So a little lab action tomorrow should be a good day. And what else? Tomorrow you get a full block, so we'll get into some problems with this stuff. Yeah, we'll have a good day tomorrow. All right, folks. See ya.